Turns out I'm walking around all day long with this little tiny freaking pebble stuck in my shoe. It does suck.
That
you know
sucks.
what else sucks?
You know what sucks?
Decon, not just decon, metering, response options, refreshers. They all suck when you're not being taught by the hazmat guys. So why should you have us come in and do your training?
Because we deliver experience and not just plain and boring and uninspiring training. When we come to train, we won't deliver a course designed years ago. Every course is updated for fresh takes and emerging trends. So doing this takes time and effort.
Yeah, and we end up partnering with other companies that are going to be with us, whether it's their equipment or their ideology or even sometimes their people, to help the training suck less.
Right. So we're going to guarantee our instructors keeps everybody engaged, and we only partner with the best in the field. So don't let your potential go untapped. Choose us as your training partner and embark on a personal and professional growth journey. Contact us now by going to thehazmat.com/hire us to reserve your spot and start your training. Good times.
Refreshing root beer in one of our tumblers with our little Timmy logo on it. Anyway,
high quality H2O. We have, you know what? I gotta say, we had the hazmat specialist happy hour the other day. Had a couple of gents on. Actually, I was outnumbered. I think I was the only guy from the United States there. Yeah, it was all Canadian, and I'm sorry, Hawaii. He is the United States. I forget. But we were talking about those wildfires,
what about the wildfires? Anything on a hazmat level about the wildfires?
We were talking about the batteries. That's a big deal over there. Which we're going to have a couple of episodes on what happened.
Okay,
because that's still happening. About how they're handling the lithium-ion batteries, because it turns out that like everything in Hawaii has lithium-ion batteries. Every house has solar, Tesla walls, everything has batteries in it. And now because the fires went through, there's some variation of compromise in every cell that's out there. So we had a long discussion about it. It was well worth
any of the conversation about like blue lasers and like conspiracy theories that have been being thrown out there. I swear to God, like people are saying Hawaii was burned down by blue lasers from the sky. So, no, okay.
Oh my God, no, we didn't have anything like that. It's just, you know what, we're doing these recordings in bulk now for all you out there in the interwebs, because we are recording like madmen to go back into the early days of recording, and that were only audio only, and we're putting video to them, and we're building out an LMS.
Yeah.
Insane. It's going to be crazy.
Taking pretty much all the content. We have figured out a really great way to turn it into a learning model to be able to fit things like refresher trainings. Just generalized, hey, we want to drill on this week. Okay, we're going to go to the hazmat guys and let's pull up this topic and we're going to drill on it. So a lot of good things on the horizon. Always good things on the horizon. We always have a horizon. Not a lot of people can say we. And if people wanted to look ahead to the horizon to find out where we're going to be, what conferences we're going to be at, what kind of things do they have to look forward to? Places, times, events.
Let's see. In order, I think we have Indiana and Oklahoma, and then Florida. I believe are the next three in list. I really should make a better list for this. I built this better, but I will be more prepared. I say that every week. I will say that every week.
Today's, you never know where the inspirations for shows are going to come from. And the inspiration for this show came from a very oddly looking shaped plume model that we were showing and talking about on the roundtable the other night. One guy thought it looked like a beautiful succulent booby, and another person thought it looked like a person wearing a bikini. Either way, it got me thinking, right? There were all these variables, and it's so interesting how these plume models can take these variables. I wanted to understand better what exactly the factors were that influenced how a chemical did what it did. Because even during our conversation, it was an ammonia release. And we were talking about the humidity, we were talking about the temperatures, and what is it that ends up putting chemicals where they end up coming? And the dispersion of gases during a chemical release is influenced by so many different variables, right? Whether it's the environment that's around it, the chemical and physical properties itself, the weather, the terrain. Understanding how things like the weather and chemical physical properties is going to influence where a chemical is going to go, that might be something that's crucially important to be able to make that split-second decision, right? Like I arrive on scene, something's happening, I do a quick chemical physical properties. I don't have time to break out my plume modeling software or wait for the weather station to arrive. I want to make the best possible educated guess based upon a certain set of variables.
I like that. I think it's very applicable, to be honest here. I mean, for the first one we're going to go through is wind speed and direction. Impactful. Right? Wind. It is. And it's something that I think everybody thinks about in some way. We use wind. It helps and hurts us because sometimes it's really good because it disperses gases, and sometimes it hurts us because it disperses gases. So the direction, the distance that the gases will travel is all induced by that. So high wind speeds can really dilute and disperse gases over a large area, reducing the concentration. And conversely, low wind speeds can result from slower dispersion and may lead to the accumulation of gases in lower lying areas.
A similar way, a different way of saying the same thing is that the wind direction is going to dictate the path of dispersion. Which it may not seem like it's saying the same thing, but it really is, right? Gases downwind can affect populated areas, but how it comes out. If anyone's ever, and I highly recommend you do, oh my God, it was just in my head and now it's gone. The chlorine release in the desert, Operation Jackrabbit. Jackrabbit 2. When you watch those videos, you see the plume is solely affected by wind, at least the shape, right? The direction of the path and the shape of the cone is primarily directed by the wind. If there was zero wind, there'd be a completely different dispersion pattern. And I think that's pretty intuitive to us. I don't think we need to really dive much into wind. You blow on something, it moves around.
Right. Now, another one, the Captain Obvious is thrown out here is temperature. Right. Temperature affects the buoyancy and the vertical distribution or dispersion of gases. So in this thing, we said this many times, things that you assume that go up or things that should go down, temperature is going to modify that. That's like the correction factor on it. So warm air is less dense than cold air, causing the gases to rise more easily. And this can result in a plume rise where the gas cloud may ascend to higher altitudes before then hooking and going horizontal.
Unless it depends kicks in and you have a temperature inversion. Right. And this is where you have like a kind of like a layer of warm air that is trapped by cooler air near the ground. And what this does is this inhibits vertical distribution. So things are less likely to go up during a temporal inversion. This is going to cause all the gas to remain close to the surface, which means that it increases your likelihood of exposure risk because that chemical is going to be sitting around for a lot longer than it normally would. And there's, you think about the things that you think about the variables, right? Oh, temperature. Well, what things affect temperature? Because this is where we start to have to play the different variable games, and daytime heating is something that would affect temperature, right? We have changes as this incident can occur. We're going to have changes in the temperature because the temperature is never just static for an extended period of time. It's always changing. So being able to predict what's going to happen in the future, that's a huge, critical thing that hazmat technicians have to do. And understanding that during the day, normally things heat up, right? The sun is going to give energy to the earth. It's going to create thermal at the ground level. It creates thermal uplifts. The ground gets warm, the air gets warm. Because the ground gets warm, the hot air rises, and that is going to bring things up. So you have temperature inversions happening, you have heating from the ground that's happening, and you kind of have these like battle of physics, battle of kind of that not conductive. Whoa, you have convective. There we go.
Convective.
You have the battle of convective currents, where some want to go up, some want to go down. Temperatures are changing as a gas is going up. Its temperature is changing. It may now want to start to come back down after being in the higher altitudes. So a lot of different variables, even within the variation.
All right, I got a trivia question for you, because I remember this word from way back when we had an episode on weather in hazmat with Bob Metcalf, and he used the word of daytime, and this is why the ERG has a daytime evacuation and a nighttime evacuation, and people are like, oh, it's because of occupancies or people being home. The term, what is the term for the day sun mixing?
Don't know.
Diurnal mixing.
Never got that. I feel like I could take the SATs.
There you
again.
go. Yes. So along with that, increased turbulence and vertical mixing in the atmosphere can help disperse gases more quickly. And we're talking about the same turbulence that you experience in an airplane. There's just like less pressure over more pressure kind of pockets. Not only that, but wind patterns might change as the result of diurnal mixing and affect the direction and the speed of the gas dispersion. So at night, when daytime, it's typically a little bit windier, and at night it's less windy typically, but also you have the cooling there, right? So when you have evening and night cooling, the absence of the solar heating can lead to cooling of the surface, and this cooling can make completely different.
Yeah, especially that affecting that temperature inversion that we talked about. It's much more likely to actually occur at night, when that layer of trapped air and cool air kind of start to intermingle. So when at night our wind speeds tend to decrease, right? We had mentioned before that wind can help disperse. So now you have a situation, let's say you're transitioning from one to another, right? We have to think about these things. Oh, it's day now, it's going to be night in a few hours or so. What could potentially happen? What things do I need to plan ahead? You could be a situation where you don't have much of an inversion. Things are dissipating quickly, and then all of a sudden you're like, "Oh man, you taste ammonia? Like, do you smell that? What is happening? Things are starting to build up." Well, you had a change in the nighttime cooling.
I like that. Yeah, and those transition times, they really, because now you're in between the cooling and the slowing. So you have, it's going to get real complex. And the thing is, do you really need to read into it? I am not, I'll be honest with you, as a technician, I never really was like, wait a second, the sun goes down at 6:23 and the tides are coming in. I never did that. I just kind of read the tea leaves and just said, okay, where we are is.
Factors, right? What do we talk about with conversion factors? You need to understand they exist, that they can be a thought in your brain. Like you said, I read the tea leaves. Well, you got to have the goddamn tea leaves in the tea to read. If you don't realize that things could change, right? Like you were talking about the transition period going from dawn and dusk. If you're not aware that things could potentially change, you might not even have the leaves in the tea to read. And that's where this stuff becomes important. It's the understanding it exists, so that you go from not knowing that you don't know what you don't know to knowing that you don't know what you don't know. I was hoping you'd hit that button. Okay.
I love it.
Yeah.
Oh, you want that?
We also have, especially coming from the city that we came from, which literally had its own potential for weather patterns. you have to be very aware of local effects of temperature conditions, right? What tends to happen in my area, in my city? For us, we were urban. Everything was streets and blacktop buildings. So naturally, we would have a bubble of very, very, very hot, humid weather, and that would play an effect on how things would be released. The time of day in a specific area, when you kind of mix that in with the topography, especially in the city, where wind patterns can change between buildings, you can get extremely localized temperature difference that completely change your dispersion pattern.
Yeah, it was really weird because you used to have, they couldn't, like that, when we say about plume modeling, I can honestly say I don't think we ever plume modeled anything because, especially in Manhattan, because you would have an easterly breeze going on the avenues, and you'd have a southerly breeze going on the streets, and it would change depending on what section you were in. So, like, you can have your own wind patterns, dispersion models. It would change going around a corner.
Yeah,
a totally different weather pattern there.
Yeah, going it was literally really left. Like you walk around the corner, you got a breeze on one side of your face. You walk around, now the breeze is on the other side of your face. It still is. All right. One thing that we talked about during that ammonia release breakdown was humidity. Right, we were talking about how does ammonia, does it go up, does it go down? But in humid weather, it tends to stick to the ground. Humidity refers to literally the amount of moisture in the air. High humidity levels can absolutely affect gas dispersion by literally increasing the gas density and reducing the speed at which they rise. It literally, it suppresses it, right? It's going to suppress those vapors. Moist air is denser than dry air, which can, again, lead to that more localization and concentration of gas plume.
So, humidity really grinds my gears because conversely,
this is a hazmat show.
Low
it doesn't grind your gears;
levels.
It breaks your bonds.
Oh, that's good. That's the new slogan. All right. So it could result in faster dispersion in the air as less dense and gases rise more quickly. Now, gas density is also intermingled with this humidity thing because it affects the density of air. Right, so moist air is less dense than dry air because the vapor molecules are lighter than the molecules of nitrogen and oxygen that makes up the majority of the atmosphere.
Literally goes to affect the buoyancy of the plume. Gases released in high humidity air, they tend to, again, rise more slowly due to that reduced density. So here we're seeing the effects of other variables on other variables. If that kind of makes right, like it's compounding. That's why the plume modeling is so important, right? It's so hard to get a good plume model because there are so many different variables at play, and all of this kind of tends to really come into effect when we talk about the plume rise, right? Because we don't often think about what is this particular molecule doing. We often think about what is the group of them doing. And in low humidity conditions, right, as we said, those gases released in the atmosphere, they tend to be more buoyant. So they're going to go up and so the plume is still going to disperse out, but it's going to go up faster than it's going out. So you can almost start to get that three-dimensional view of how big it's getting as it's going up and hitting those higher altitudes.
Now, conversely, in higher humidity things, moist air, gases have less buoyancy and may not rise as rapidly, and this can lead to a lower plume height. So I like knowing a little more than I'm kind of learning a little bit on this one. So the concentration gradient, because we think about these like plumes, it's like you got to remember that there is a point where it starts at 100 and it feathers out. Right. And so it's not like there's a finite line. They kind of have this
blow up a balloon in the
right. Exactly. Right. It's not right up against the wall. So the concentration gradient of a gas plume is influenced by specifically humidity. In dry conditions, gases may disperse more rapidly, leading to a more uniform distribution and lower concentrations at the source.
Conversely, in humid conditions, gas plumes disperse more slowly, resulting in a more concentrated plume near the release point. Now, how does that play into our operation? Well, understanding that if you're turning around, you're going, well, I'm only getting 5 parts per million here. Understand that a few feet away, because that plume has a higher concentration gradient, you're going to go into higher levels much more quickly. Whereas a nice dry area, you may have 5 over here, 5 parts per million here. 15 feet away, you got 6 parts per million. It disperses out evenly. So we talk about these things, and yes, the plume is the plume, but there's concentration gradients inside the plume, which affects how we meter. It affects what we would predict to happen, and it affects how we tend to think about what is going to happen in the future and how to get people in certain areas to get the as best of readings as possible.
Just remember, it's on an X, Y, and Z axis.
Yeah, and
you got to consider
multiple
these
dimensions. It's not X, Y, Z, and time, right? So it's just there's so much going on. How does humidity affect the chemical reactions? Right. This was a mailbag question from your other day. Some chemical reactions, they react with the water vapor in the air, potentially changing the properties and forming a new compound. Humidity can absolutely influence the rate of the reaction, right? It helps drive a reaction in one way or another. Great example of this would be like an acidic gas. It reacts with the water vapor. It now forms an acidic aerosol, which can affect the behavior and have health implications far down the dispersion path that we would not have normally thought of.
Now, we kind of went into the topic of rainfall in the last couple of inclement weather episodes, but when you have extremely high humidity, which once you start getting up almost 100, you are raining, so it may be associated with some rainfall. So rain can help move chemicals from the atmosphere by just basically scavenging them out of the air and depositing them on the ground or into bodies of water. And so this could be both a benefit by reducing your exposure risk or detrimental by contaminating the water source.
From a response point of view, especially when we talk about that transition or temperature changes, as we start to now mush variables together, high humidity can reduce visibility. So from an operational point of view, understanding that you don't have a good big picture view of what's happening makes operating on a scene much more challenging to assess the plume itself, assess its direction, monitor for its movement. And a lot of times, we talk, especially electrochemical sensors, sometimes sensors that rely on resistance, like give me a second to think about it, the negative corona discharge. They can be massively affected by humidity. So all this needs to be taken into account when you're operating